So today I'm going to take a very basic part of the organic chemistry. And as we all know that what exactly organic chemistry is. So organic chemistry is basically when the carbon interacts with hydrogen. So the hydrocarbon interaction is what is called the organic chemistry. The chemistry of carbon and all compounds with which it is reacting. So as I mentioned here that there are 5 million organic compounds which exist, and this is because the carbon, which is so versatile, it is having a tetravalent valency, and that is why it can form covalent bond with any element. Okay, so first of all comes to the basic definition of organic chemistry. So actually it is the branch of chemistry because there are three different types of branches of chemistry: organic, inorganic, and physical chemistry. So here we are basically discussing the organic chemistry part that deals with carbon and its compounds, such as if carbon form a bond with the calcium, so that will be calcium carbonate. If it form the oxides, then that will be carbon monoxide, carbon dioxide. And then if it form carbides, titanium carbide, mercuric carbide. So it is the branch of chemistry which involves the study of nomenclature. Now, what exactly nomenclature is? So nomenclature is naming any chemical compound with its structure and properties like boiling point, melting point, how it is reacting with any specific reagent. So such reactions are also involved in organic molecules. Okay. So just now I told that carbon is tetravalent. We know that the electronic configuration, ground state electronic configuration of carbon is 1s to 2s to 2. Okay. So but what happens in the excited state? The 2s electron goes into the p orbitals because we know that this p orbital over here, there are three p orbitals: px, py, and pz. So px and py are half filled because one electron is there in both the orbitals, and pz, the 2s, one electron will go into the pz orbital, and that is why carbon over here is showing the valency of +4. Okay, so now we'll see that how the carbon is forming different bonds like alkane, alkenes, and alkyne. What exactly they are? When carbon is attached to a different carbon with a single bond, that is what is called alkanes. When carbon is attached to a different carbon with a double bond, that is what is called alkene. And when carbon is attached to the triple bond, that is what is called alkyne. So now we'll look at the hybridization. When the single bond, in the case of alkane, the hybridization is sp3 with the geometry of tetrahedral. Okay, tetrahedral you can see over here, like every angle, bond angle is 109.5 over here. So every angle will be 109.5 over here. If you consider like tetrahedral, which is forming 4 angles, so all the 4 will be of 109. So if we talk about the S character over here in the single bond, sp3, so okay, so 25% will be S character and 75 will be P character. So in case of alkenes, in the double bond character, where the sp2 hybridization is there, so the geometry will be trigonal planar over here. In trigonal planar, each and every angle is of 120 degree because 12, 120, 240, and 360 makes the overall angle. Here, if we talk about the S character, that is 33.33%. Now, next comes the triple bond. Triple bond is there in case of alkynes. Alkynes make a sp hybridization, which is linear. Linear is like if we talk about the S and P character over here, S character is also 50% over here, and P character is also 50%. So this makes the bond angle of 180 degree in case of alkynes. So if the carbon is attached to a single carbon, there also it is making an alkane. Then carbon double bond carbon is alkene, and carbon triple bond carbon is alkyne. These are the orientation in space of these hybrid orbitals. Like I told you, the single S and single P orbital will make a hybrid orbital. What are hybrid orbitals? Which are combined, which are mixed by two different orbitals. Such as we can take here the example of 1s and 1p orbital combined together to form a sp orbital. Then comes the sp2 hybrid orbitals. In this case, 1s and 2p orbitals the one electron of the s orbital goes into the pz excited state, and it takes the two orbital px and py. Therefore, in sp2 hybrid orbitals, 1s and 2p orbitals are involved, and the pi bond has been formed by the pz-pz overlap. In sp3 hybrid orbital, 1s and 3p orbitals are involved, px, py, and pz hybrid orbitals, so as to combine to form sp3. Now, structural representation of organic compounds. So, this is the structure of methane. I can represent it in three forms: dash form, condensed form, and bond line structure. So, dash form, as I represented in this figure, that methane, the carbon is attached to 4 different hydrogen in the form of a dash. Dash is the structure that is used to show the covalent bonding between carbon and hydrogen, because they have formed the bond by sharing of electron. Hydrogen is sharing its 1 electron with the 4 electrons of the carbon. So the number of dashes indicate whether the bond is single, double, or triple. Okay, if there is single double bond, so the single dash will be there. Consecutively, if there are triple covalent bond, then 3 dashes will be there. Then condensed structure is there. It simply does not show the covalent bonds. It is the condensed structure like ethane. So we'll simply write as CH3, or we can write as C2H6 in the condensed structure, where we do not mention the double or triple bond. Just it is represented in the form of carbon and hydrogen. And by looking at the formula, like if carbon's valency is not satisfied, then we have to apply a double bond or a triple bond. Like here, in case of ethyne, like if two hydrogens are present attached with the carbon, and we know that to settle carbon has a valency of 4, so we had to satisfy. So these 2 electrons were taken by forming the double bond in case of ethyne. Like bond line structures are there, which just represent the structure by lines, and usually the terminals are always methyl groups, unless and until they are specifically stated that any other functional group has been attached. Like over here in the structure 1 and 3, it is the structure of pentane, because if we name the carbon as 1, 2, 3, 4, and 5, so 5 stand for pent, and this is for alkane, so this will be pentane. Now in the second structure, at the second position, there is methyl group. We'll see in the nomenclature, IUPAC nomenclature, that we give priority to the methyl group attached. We will not take it from the right, but we'll take the naming from the left. So here, 1, 2, 3, 4, and 5. So this will be 2-methyl pentane. Pent is the basic ring basic straight chain, and it is alkane, so pentane. And at the second position, methyl substituent is there, so this will be 2-methyl pentane. Now in the fourth structure, we look at the fourth structure. At the second position, there is methyl substitution, but it is a 4-membered ring. So this will be butane, okay, because 4 carbons are there. So methane, ethane, propane, and butane. 2-methyl butane will be there. Now we come to the classification of organic compounds, because classification is very necessary so as to ease out the things, because it will be very complex if you consider 5 billion organic compounds which are formed by carbon. So basically they are classified in acyclic and cyclic compounds. Cyclic compounds are those closed ring, and acyclic compounds are open chain. In acyclic compounds, we can look at the example of ethane, methane, propane. And in the cyclic compounds, they are further classified into 2 types: homocyclic and heterocyclic. Homocyclic are those which are having only carbon atom. Like if I am talking about this cyclopropane ring, then all the compounds will be okay. So like if I'm talking about the cyclopropane ring, then all the compounds over here are made of carbon and its compound. But if I talk about the heterocyclic ring, then there can be nitrogen, oxygen, sulfur, any heterocyclic compound, like other than carbon, phosphorus, like Halogens can be there, which can be fluorine, fluorine, bromine, iodine. Okay. So in homocyclic, only carbon-anion compounds are there, like all the ring structure is made up of carbon. And in heterocyclic compounds, there can be compounds other than carbon. Okay. So if I'm taking homocyclic compounds, okay, they can be of two types. Next, like alicyclic and aromatic. Alicyclic are those which do not follow Huckel rule. Okay. So what is Huckel rule? Huckel rule is the 4n plus 2 rule. Like there should be 4n plus 2 number of pi electrons in any system. Okay. So like here in cyclopropane ring, there are no pi bonds are present. Okay. So it does not follow any Huckel rule. But if we talk about the aromatic system, benzene is the perfect example. Where in benzene, it follows the Huckel rule, which is if any compound is aromatic, then it has to follow the Huckel rule, which should be the number. Pi electron should be 4n plus 2. So 4n plus 2, if I talk about benzene only, it is having 6 number of pi electrons. Okay. So in heterocyclic compounds, furane and pyrrole, there are many examples. Furane is having oxygen as a heterocyclic compound. And in pyrrole, nitrogen is there as a heterocyclic compound. Okay, so like this, these are the, like with sulfur also, thiophene is there. With chlorine, it can be a chlorobenzene, fluorobenzene, bromobenzene. So like these are the heterocyclic compounds. Okay, so in cyclic or closed ring compounds, there are two types of compounds, homocyclic and heterocyclic, and these are further classified. So, Huckel rule. Huckel rule, just now I was telling about the aromaticity. It tells about that whether the compound is aromatic or not. Okay, so if any planar ring molecule will have aromatic properties if it has 4n plus 2 number of pi electrons, where n is a non-negative integers. Okay, so now comes to the IUPAC nomenclature. IUPAC nomenclature is the standard international standards. Okay, so like if I have to name something, so in different places the naming has to be different. But it will be very difficult for me if I'm talking to someone in the different language. Okay, so I won't be able to understand their language and they won't be able to understand my language. So there has to be an internationally accepted standard nomenclature system for the naming of these compounds. So this IUPAC nomenclature system has been set up. And the purpose of this system is to establish an international standard of naming compounds. Okay, so like there will be no misunderstanding between compounds. Like if I say ethane over here, so by following the IUPAC nomenclature, it is ethane worldwide. Okay, to facilitate communication. The goal of the system is to give each structure a unique and unambiguous name. Like no two structure will have the same name with this IUPAC nomenclature. Okay, so unique and unambiguous name. And to correlate each name with a unique and unambiguous structure. So structure is also different. Okay, so the fundamental principle of IUPAC nomenclature is based on the meaning of molecules' longest chain. Okay, so if the basic structure or the fundamental principle is this, that the molecule's longest chain of carbon connected by a single bond, whether in a continuous chain or in a ring. Okay, so like if I have a 6-membered ring, so I'll call that as hexane. Okay, all deviations, either multiple bonds or atoms other than carbon and hydrogen, are indicated by prefix or suffix. Like if I have in a carbon chain of 6 molecules, at the second position, I have a double bond. So what I will say, hex to ene. Ene is there for double. That will look. Prefix and suffix are adding before and after that specific carbon chain, so as to mention the number of functional groups, double bonds, triple bonds, or any other moiety which has been attached to that ring or a carbon chain. Okay, so first of all, we'll look at the alkane and cycloalkanes classification. Alkanes are saturated hydrocarbon, means they don't have any double or triple bond. Okay, so that is the molecules containing carbon and hydrogen connected by single bonds only. These molecules can be in continuous chain, they can be in a linear form or a acyclic form. Just now we read about the acyclic form of cyclopropane over here. Okay. So they can be in the linear form or the acyclic form, or in the ring form, cyclic or alicyclic. Okay. So in the cyclic form or alicyclic form, they can be in the ring form, cyclopropane, cyclopentane. Ethane, we cannot make the structure as a ring because it has just two carbons. The name of the alkanes and cycloalkanes are the root name of organic compounds. Okay. If it is in the ring form, then you have to add cyclo, or it is in the linear or acyclic form, then you have to just mention the alkane root. Okay. Beginning with the 5-carbon alkane, the number of carbon in the chain is indicated by prefix. Okay. Like rings are designated by the prefix cyclo. Okay. And the geometrical symbols for ring, each apex represent a carbon with the number of hydrogen which are attached to fill the valency, because carbon has a valency of 4. So we have to, in the geometrical symbol, we have to fulfill the valency of carbon by attaching the hydrogen at the apex point, at the tip point. Okay. So naming of organic compounds. The increasing large number of organic compounds identified each passing, because the research is going on today with the fact that many of these compounds are isomers of other compounds. Isomers are those which have the same molecular formula but differ in structure, can have a different functional group. So these are the various types of isomers. We will discuss them later. Requires that a systematic nomenclature should be developed. Okay, so like we had to develop a systematic nomenclature. Just now I told you before the previous slide. So just as each distinct compound has a unique molecular structure which can be designated by a structural formula. Okay. So in organic chemistry, we developed some of the examples, and these were used previously, like trivial names were there, which were before the IUPAC nomenclature. That is why the need of IUPAC nomenclature came, because the trivial names were based on the previous names or the uses. Like if I will talk about the butyric acid, then it came from butyrate. If I talk about the citric acid, it comes from citrus fruits, like this. Okay. So some common names often have their origin in the history of the science or can be from the natural product. Just now I mentioned the example of citric acid that comes from the natural product as citrate. Okay, so from citrus fruits, like this. Okay, but the relationship of these names to each other is arbitrary and no rational or systematic principle underlies their assignments. Okay, so relationship is totally individual and is totally different. Like if I talk about a carbon having single carbon is known as meth. Okay. And ane is used for alkane. 4 carbons are known as butane. Acetone is there for CH3COCH3. Toluene is when your benzene ring is attached with a methyl group. Acetylene is when your ene has came, so it's an alkene. And in methyl alcohol, it's C2H5OH. Hydroxy functional group has been attached to the ethyl group. Ethyl is when C2H6, the hydrogen has been replaced by a functional group. So this is ethyl. Okay. So rational nomenclature. Okay. Rational is new. Nomenclature should do at least 2 things. First, it should indicate how the carbon atoms of a given compound are bonded together. Okay. It should specify the position where they are bonded, where there is a single bond, double bond, or a triple bond, and the characteristic lattice of chain or ring, or is there any chain or ring is there. Second, it should identify and locate any functional group present in the compound. Okay, just now we discussed. Since hydrogen is such a common component of organic compound, its amount and location can be assumed from the tetravalency of carbon. Okay, so like hydrogen is very common component in every organic compound. What we do, we assume that the carbon is tetravalent and then we satisfy, okay, the valency of carbon by adding the hydrogen. And that is why hydrogen need not to be specified in most cases. In most cases, you are not supposed to specify the number of hydrogens. You just write the number of hydrogens. You don't need to specify the hydrogens. The IUPAC nomenclature system is a set of logical rules devised and used by organic chemists to circumvent problem caused by arbitrary nomenclature. Like previously, travel, like we just discussed over here. Previously, what used to happen, arbitrary nomenclature, or in the history times, in the past times, trivial names were used. So that is why the IUPAC nomenclature came. so as to circumvent with the problems associated with the previous or the arbitrary nomenclature. Knowing these rules and given a structured formula, one should be able to write a unique name for every distinct compound. Likewise, given a IUPAC name, one should be able to write a structural formula. So, what are the three necessary and essential features to write the IUPAC name? A root or base indicating a major chain. Okay, so first of all, there has to be a major chain or a basic root or ring of carbon atom found in the molecular structure. A suffix or other element designating functional groups. Okay, suffix are those which are added after. Okay, so like if I had a functional group which I can take as hydroxy, so ol will add as a suffix after the chain. Okay, that may be present in the compound. Name of substituent group other than hydrogen that complete the molecular structure. Okay, so like if there is any other substituent such as methyl, ethyl, chloro, cyclo ring is attached to the main ring. So all these substituents other than hydrogen, then we had to complete the molecular structure. Okay, as an introduction to IUPAC nomenclature system, we shall first consider compounds that have no specific function. Only the plain chains we will discuss first. Such compounds are composed only of carbon and hydrogen. Okay, so these are the basic chains. And I know, and we all know that single bonds are sp3 hybridized carbon. Okay, all carbons will be sp3 hybridized and they will have a sigma bond. Okay, sigma bond is a single bond. And in sp2 hybridized carbon, where C double bond C is there, that is what is called pi. And in sp hybridized carbon, where C triple bond C is there, so it will have a 2 pi bond and 1 sigma bond. So now we are talking about the sp3 hybridized carbon, which are alkenes. So hydrocarbon having no double bond, triple bond functional group are classified as alkanes or cycloalkanes, depending on whether the carbon atom of the molecule are arranged only in chains and also in rings. Although these hydrocarbons have no functional groups, that is why we are calling them as alkane, okay, because there is no functional group except carbon and hydrogen. They constitute the framework on which functional groups are located in other classes of compounds and provide an ideal starting point for studying and naming organic compounds. So, if we know that alkane are having no functional group, they constitute the framework on which functional groups are located in other classes of compounds. Okay, so I'll provide an ideal starting point for studying and naming organic compounds because these are very easy class of the organic compounds. The alkanes and cycloalkanes are also member of larger classes of compounds referred to as aliphatic compounds. Aliphatic compounds are compounds that do not incorporate any aromatic ring in their molecular structure. Okay. So aliphatic and aromatic, these are two different things. Aromatic are having a ring structure, whereas aliphatic are straight chain compounds. And cycloalkanes are those in which the cyclic structure has been present with a single. Then the following table, which will come next, is considering all the basic moieties or basic ring when you have to apply by looking at the chain number of compounds present from carbon 1 to carbon 10. A common ane suffix identify these compounds as alkanes. Longer chain alkanes are well known and their names may be found in many references and textbooks. The names methane through decane should be memorized. Methane is carbon 1 and decane is having a carbon 10 structure attached with hydrogen and with fulfilling its valency of 4. Since they constitute the root of many IUPAC names, fortunately common numerical prefixes are used in naming chains of 5 or more carbons. Okay, so like this, here I mentioned some of the unbranched alkanes. Meth is used for 1 carbon, ethane, pro, but, pent is used for 5. So, and here the number of isomers are also given. Because still propane, there can be no isomers. But in butane, isobutane and neobutane, these are the two isomers of butane. And in pentane, isobutane, neobutane, and there can be 2,2-dimethyl pentane. That is neopentane. Then hexane, there are 5 isomers with 6 members. Heptane is 7 carbons. Octane is 8 carbons. Nonane is 9 carbons. Decane is 10 carbons. So CnH2n plus 2 is the basic formula for determining the formula for the carbon and hydrogen structure in alkene. Like over here, CnH2n, if I apply in methane, so Cn will be 1 and H2n will be 1 over here. So 2 into 1 plus 1 will be 2 into 1 plus 2 will be 4. So CnH2n plus 2. CnH2n plus 2 is for alkanes. CnH2n is there for alkenes and CnH2n minus 2 is there for alkynes. So over here I am talking about alkanes. So if I put N value as 1 in methane, so that will be CH4 over here. Okay, so this was the formula I was talking about for alkanes. Some important behavior trends and terminologies. The formulas and structure of these alkanes increases uniformly by a CH2 increment. Okay, so like we were talking about methane, ethane, so there had been just an increment of CH2. And we know that carbon is having a molecular formula of 14 and hydrogen as of 2. So this gives carbon has an atomic molecular formula of 12. Carbon has a molecular mass of 12. So 12 plus 2 will give you 14. So there had been an increment of 14 atomic mass, molecular mass. A uniform variation of this kind in a series is called as homologous series. So like there is CH2 increment uniformly in every individual element or molecule which has been stated above. This shows that the molecular formula is CnH2n plus 2 and it is following that rule. This is also highest possible. So these formulas all fit the CnH2n plus 2 rule. Okay. So hydrogen upon carbon ratio for a stable hydrocarbon. This also is possible. And since hydrogen upon carbon ratio in these compounds is at maximum, we call them saturated. Okay. Saturated means having a single bond. Okay, with hydrogen. That is why these are called as saturated, and unsaturated compounds are those where they are not having any single bond, they are having a double. Okay, so like saturated and alkene and alkyne both will be called as unsaturated. Only saturated compound is this alkenes. Okay, so beginning with butane. Butane is having a 4 carbons. Okay, and when we apply the CnH2n plus 2 rule, so it will have a 10 number of hydrogen because 4 into 2 plus 2. Okay, so 8 plus 2 will be 10 and becoming more numerous with natural alkanes. So we are showing the various isomers of butane which can be possible. Okay, so here 5 isomers are possible for butane. Simply this single structure butane where we didn't do anything, like we just mentioned the carbons, and like these are for butane. And for example, over here I have mentioned for hexane also, like 6 carbon chain is there, and 6 to the 12 plus 2 is 14. So number of hydrogen will be 14 over here. Okay, so there are 6 isomers of hexane. First is the single straight chain. Then at the second position, in the second group, there is at the second position methyl substituent is there. At the third structure at third position, the methyl substituent is there. And in D structure, what is there at second position? 2 methyl substitutions are there. And in the E structure, at first and second position, there are 2 methyl substituents. Okay, so like this, we can draw 6 structures of hexane. And here at E structure, what we will name as, start the naming from here 1, 2, 3, and 4. So at 2, 4, there are 2 methyl substitutions. In D structure, what we'll name as 1, 2, 3, and 4. At second position, 2 methyl substitutions are there. So IUPAC system requires first that we have names for multiple. Okay, so like unbranched chains, branch chains. So what are the basic structure? Like if I'm having a single moiety, methyl is there. for 2 carbon ethyl, for 3 carbon propyl. If propyl has a isomer which is isopropyl, then butyl is having a isomer, isobutyl, secondary butyl, tertiary butyl, because if the carbon is attached to two different carbons, 2 carbons, then it is a secondary butyl. If it is attached to 3 carbons, if it is, then it is tertiary butyl. So likewise, various alkyl groups are there. Alkyl groups are, why these are alkyl groups? Because one hydrogen has been replaced by any other functional group. Okay. So like this, as noted above, and second that we have names for simple alkyl groups that may be attached to the chains. Okay. So for example, some common alkyl groups are given in the following table. Note that an suffix is replaced by "-il" in naming groups. The symbol R is used to designate a generic or alkyl group. Okay. It can be any alkyl group. So basic nomenclature rules for alkane moiety. Okay. So first name the longest and continuous carbon chain. It has to be continuous. Like when we were looking for the isomers of hexane, so we looked in the E structure for the continuous chain of hexane. Identify and name groups attached to this chain. Now, what we will do? We identify that 2 methyl groups has been attached at the second and the third position. Okay. So number the chain consecutively starting at the end nearest the substituent group. Okay. So how we are supposed to number the chain? We have to number the chain starting at the end which is nearest to the substituent group. Okay. So like if there is substituent at the second position from the left side and that single substituent is coming at the third position from the right side. So we have to give priority to the left side. Designate the location of each substituent group by an appropriate number and name. Okay. So we have to substitute each substituent group. We have to give the location by providing the number. Like we have to do proper nomenclature and naming of that compound. Assemble the name listing group in alphabetical order. Like if cyclopropyl is given and isobutyl is given, so C comes before. So cyclopropyl will be given more priority than isobutyl. Same with the case for methane and ethane. Ethane will be given priority more than ethane. Then methane.